Imagine a material so thin, it is literally one atom thick. A flat, single layer of carbon atoms, arranged in a perfect honeycomb lattice, kind of like a microscopic chicken wire. This isn't science fiction, this is graphene. It was hiding in plain sight for centuries, in every pencil stroke you've ever made. The graphite in your pencil is just countless layers of graphene stacked together, almost like a cosmic deck of cards. But in 2004, scientists finally managed to isolate a single sheet. They used a surprisingly simple tool-ordinary sticky tape. This humble discovery unlocked a universe of possibilities, revealing a material with properties so extraordinary, they seem to rewrite the rules of physics and materials science. So what makes this simple carbon sheet so special? It all comes down to its incredible structure and the behavior of electrons within it. Graphene is the strongest material ever tested, stronger than steel, yet it's incredibly lightweight and flexible. You could, in theory, create a hammock from a single sheet of graphene that could support a cat, yet the hammock itself would weigh less than one of the cat's whiskers. It's also an exceptional conductor of both heat and electricity, allowing energy to flow through it with almost no resistance. These electrons don't just move, they dance across the honeycomb in a way that mimics massless particles, which is a truly exotic quantum phenomenon. Beyond its strength and conductivity, graphene has a fascinating relationship with light. It is almost completely transparent, absorbing only about 2.3% of the light that passes through it. Think about that for a moment. A material made of pure carbon, the same element that makes up dark charcoal and diamonds, can be virtually invisible. This transparency, combined with its other unique electronic properties, sets the stage for a new kind of technology. It allows us to build devices that can interact with light in unprecedented ways, all on a scale thousands of times thinner than a human hair. Graphene isn't just another material, it's a new canvas for manipulating the very fabric of light. This single layer of atoms is a gateway to a new frontier in physics and engineering. Its discovery was not just a scientific curiosity, but the dawn of a new age for materials. It challenges us to rethink what's possible, from super strong composites to flexible electronics, and, most excitingly, to the very way we control and guide light. We are just at the beginning of our journey with graphene, exploring its vast potential to build the technologies of tomorrow. The story of this simple carbon sheet is a testament to how the universe's most fundamental building blocks can hold the most profound secrets, just waiting for us to uncover them. To understand graphene's power, we must first explore a beautiful phenomenon called a surface plasmon. Imagine light as a wave rippling across the surface of a cosmic ocean. Now, picture the electrons in a material as a sea of charged particles. When light hits the surface of certain materials, its energy can be transferred to these electrons, causing them to oscillate together in a collective, rhythmic dance. This synchronized wave of electrons, coupled with the light that created it, is a surface plasmon. It's a hybrid of light and matter, trapping electromagnetic energy and confining it to the material's surface, allowing us to guide light in ways that lenses and mirrors simply cannot. For a long time, this cosmic dance was primarily observed in metals like gold and silver. These materials are rich in free electrons, making them excellent hosts for plasmons. However, metal-based plasmonics has its limits. The plasmons they support are typically confined to the visible and near-infrared parts of the electromagnetic spectrum. Furthermore, once you fabricate a gold nano antenna, its properties are fixed. You can't easily change how it interacts with light on the fly. It's like having a radio that is permanently tuned to a single station. This rigidity has limited the applications and flexibility of traditional plasmonic devices, creating a need for a more adaptable material. This is where graphene enters our story, changing the rules of the game. Graphene supports plasmons, but with a remarkable twist. Because of its unique two-dimensional structure and its massless electrons, graphene's plasmons can confine light much more tightly than metals can. More importantly, these plasmons operate in a different part of the spectrum, the mid-infrared and terahertz range. This is a critical region for applications like thermal imaging, molecular sensing, and next-generation communications. Graphene opens up a whole new frequency window for us to play in, a window that was largely inaccessible with conventional metals, offering us a fresh playground for light manipulation. The most revolutionary aspect of graphene plasmonics is its tunability. Unlike gold or silver, graphene's properties are not set in stone. We can actively tune them, changing the number of available charge carriers within the material simply by applying a small voltage. This is like having a magical knob that can adjust the plasmon's frequency in real time. It's the difference between a fixed station radio and a modern, fully tunable receiver that can scan the entire dial. This unprecedented level of control means we can build dynamic, reconfigurable devices that adapt to our needs, heralding a new era of active photonic metamaterials. The ability to actively tune graphene plasmons is like being a cosmic sculptor of light. One of the most direct methods is electrical gating. Imagine placing our graphene sheet in a simple field effect transistor structure, similar to the components inside every computer. By applying a voltage to a nearby gate, we can either inject more electrons into the graphene or pull them out. This process, known as doping, directly changes the density of charge carriers. Since the frequency and intensity of the plasmons depend on this density, we gain a direct electrical handle to control how graphene interacts with light. It's a beautifully simple yet powerful way to modulate light on a chip. But the artistry doesn't stop there. We can also shape the light by shaping the graphene itself. Using advanced nanofabrication techniques, we can etch the continuous graphene sheet into specific patterns like tiny ribbons, discs, or more complex antenna-like structures. Each geometry acts like a unique resonant cavity for plasmons, trapping and enhancing light at specific frequencies. A narrow ribbon will resonate with light of one color, while a wider ribbon will resonate with another. It's like creating a microscopic xylophone where the size and shape of each key determines the musical note, or in our case, the frequency of light it responds to. We can even add another dimension to our control by stacking multiple layers of graphene. Think of it as creating a photonic sandwich. We can place 2 or more graphene sheets on top of each other, separated by a thin insulating layer. The plasmons in each sheet can then interact or couple with each other across the gap. This coupling creates new hybrid plasmonic modes that are exquisitely sensitive to the distance between the layers. By controlling this tiny separation, we can fine-tune the optical response with incredible precision, creating sophisticated filters or switches that operate on a scale of just a few atoms. These methods, gating, patterning, and stacking, give us an unparalleled toolkit for engineering light-matter interactions. We can combine them to create what scientists call metamaterials, artificial structures designed to have properties not found in nature. For instance, a patterned array of graphene nanoribbons can act as a perfect absorber, trapping nearly 100% of incoming light at a specific terahertz frequency. By applying a voltage, we can turn this absorption on and off, creating an ultra-fast optical switch. This level of control, from electrical tuning to geometric sculpting, is precisely what makes graphene the cornerstone of a new generation of photonic devices. The practical applications of this newfound control over light are as vast as the cosmos itself. Graphene plasmonics is not just a laboratory curiosity, it's the foundation for real-world devices that could transform technology. Consider the field of sensing. Because graphene plasmons are so tightly confined to the surface, they are incredibly sensitive to their immediate environment. If a molecule lands on the surface of a graphene nanostructure, it will slightly alter the plasmon resonance. This shift can be detected, allowing us to build ultra-sensitive biosensors capable of identifying specific proteins, viruses, or pollutants with unprecedented accuracy, essentially giving us a microscopic sense of smell. In the realm of communications, graphene offers a path to faster and more efficient data transfer. Devices like tunable filters and modulators are the building blocks of optical communication systems. A graphene-based filter could be designed to selectively allow certain frequencies of light to pass while blocking others, and its operating frequency could be changed in real time with a simple voltage. This could lead to reconfigurable optical networks that are far more flexible and energy efficient than what we have today. Graphene nanoantennas could also enable chip-to-chip wireless communication, breaking the bottlenecks imposed by physical wires and paving the way for more powerful computing architectures. Graphene plasmonics is also enabling the creation of entirely new classes of metamaterials. These are engineered materials whose function comes from their structure, not their chemical composition. By arranging graphene nanostructures in precise arrays, we can craft materials that can bend light in unusual ways, act as cloaks in the terahertz spectrum, or function as perfect absorbers for thermal imaging and energy harvesting applications. These devices are thinner, lighter, and more versatile than their predecessors, opening doors to technologies that were previously confined to the pages of science fiction. The ability to build these materials from a single layer of carbon atoms is truly revolutionary. As we stand on the cusp of this new photonic era, graphene shines as a beacon of possibility. From its humble origins in a strip of tape to its role in sculpting the flow of light, its journey is a powerful reminder of how a deep understanding of the universe's fundamental rules can lead to profound technological leaps. Graphene is more than just a material. It is a platform, a new set of tools that empowers us to see and control our world in ways we are only just beginning to imagine. The future of photonics, communications, and sensing may very well be written on a single, extraordinary sheet of carbon atoms.